Hello, everyone. My name is Janet Kelsey of Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with Agilent. Our topic today is Headspace, Shoulders, Knees and Toes, how to decide between liquid or Headspace sampling and recent improvements in Headspace technology. Let me introduce our presenters for today's webinar. Adam Bivens is the product manager of GC Headspace at Agilent. A chemical engineer turned chromatographer, Adam has over 10 years of experience in both liquid and gas chromatography products. Before joining Agilent, Adam was a customer using GC to analyze fuel cells and electrolyzers. Abby Fawcett is an applications chemist within Agilent's gas phase separation division, where she develops methods and training focused on new features released in GC and GCMS systems. Before joining Agilent in 2011, she was an Agilent customer for over 10 years, dedicated to multi-technique method development and validation. And so, without further ado, I'll turn the presentation firstly over to Adam.
Thank you so much for the kind introduction. Hello, everyone. My name is Adam Bivens. I'm going to be presenting today with Abby Fawcett for Agilent Technologies. I am a product manager for GC Headspace, and then Abby is the applications chemist on our team, also covering GC Headspace. Today, we're going to be covering Headspace, shoulders, knees, and toes, a introduction to modern Headspace technology, as well as covering the topic of how to decide between liquid or Headspace sampling with current technologies today. So without further ado, let's get started. So there are plenty of kind of myths still out in the world around Headspace. Most folks you see will approach Headspace as a type of technique that's only needed for specific applications. It often is seen as more expensive, as well as being more complicated. In reality, however, Headspace is a affordable and reliable technique that has stood the test of time and also offers significant time and labor savings, especially around sample preparation. So just to kick off our introduction, let's take a quick review of the two sampling methods in GC. Liquid sampling, which is familiar to most users, takes the sample directly out of the vial in the liquid form through a syringe, injects it into a hot inlet where it is vaporized, and then it is either partially or completely put onto the column to then flow through, be separated, and then reach the detector. Headspace sampling, the vial itself is heated to evaporate analytes, and then the gas above the sample is removed, and then that vapor is swept from the vial through the inlet onto the column. So why do labs choose Headspace when they are looking at developing a method? The biggest reason that differentiates Headspace is that it can handle just about any sample that goes into the vial. Anything from dirty samples, solids, to heat-sensitive samples, things like dirt itself, metallic samples, anything that can really pose a significant sample cleanup challenge is perfectly measurable in Headspace with very little to no sample preparation. Additionally, Headspace, because you are pulling the vapor phase from the vial, everything else stays in the vial. There's very little contamination on inlets, columns, seals, and detectors, as well as just generally less maintenance required on the system. Additionally, because you have a vapor phase moving through the system, you do not have this large amount of evaporated solvent that would be introduced from a liquid injection. That means there's a smaller solvent peak and generally less matrix interference in the analysis. This means that there's also less background, which leads to higher sensitivity with good precision and linearity across a very wide range of compounds. Considering all of this is with a sample that can sometimes be very dirty and heavy in matrix, that means that there's a lot of really good opportunities to switch over from more traditional liquid-based methods to start using Headspace. So what about your specific lab? The big question to ask is whether or not there are particular samples that really eat up a lot of time in terms of sample prep. If you could just load and crimp that sample, vaporize the analyte of interest, and measure the corresponding target analytes, would that be a significant savings for your lab? Also, are there particular compounds or sample types that lead to a substantial amount of maintenance time? In some cases, you'll see extractions that are so dirty that the inlet needs to be switched out in less than a dozen injections. These sort of analyses are perfect for Headspace. Everything that goes into the vial that's a solid, that's not volatile, stays in the vial. Additionally, you just generally are going to have less wear and tear on your columns, fewer consumables switches, and your detectors, including your sources, just generally need less cleaning. Lastly, there's a wide range of samples that can be run on Headspace. So if you're running a lab where you don't know what's coming in the door next, you'll be able to do anything from analyzing machine oil directly on the screws like you see here, all the way through to analyzing sand and soil samples. So regardless of what comes through your door, you're able to respond with, I can probably analyze that without a long difficult sample preparation work to try to find what exact method will get the target analyte into liquid form to be injected later. So here's a quick review for folks who are maybe a little bit less familiar with Headspace sampling of the key parameters when you're developing the sample introduction side of a method. On a liquid sampler, injection volume, inlet temperature, split ratio, split flow, septum purge flow, and inliner types are all things that you have to choose when you're going to be setting up a liquid-based method. In Headspace, many of those parameters have an analog that's just slightly different. Things like sample loop size, oven temperature, equilibration time, vial shaking, fill pressure, and then finally the final volume of vial and sample are really the determining factors that are going to affect how much sample reaches the column, how much time the sample needs to evaporate, and then all of the related sensitivity effects that those have on your final analysis. So where is Headspace used today? It is a time-tested technique, like I mentioned before. So you will see this in USP 467 for residual solvents, and analyzing the alcohol content in forensic samples across a wide range of different volatile organic carbon tests for both pesticides as well as petrochemicals and other types of pollutants in water and in soil. You'll see it in the food industry for flavors, fragrance, beer, dairy, and then finally, it's a major component of transformer gas analysis. So really a wide range of applications that rely on this ability to take dirty samples and with very little work and cleanup, analyze a wide range of compounds reliably and with a high degree of sensitivity and repeatability. Agilent provides a leading Headspace system through the 8697 Headspace sampler. This new generation has a number of features that allow most labs to reach their peak productivity. You have a 12 vial oven capacity, which provides the shaking and overlapping samples needed to maximize the number of runs per hour on any GC. You have a 48 vial 8697 version, the G4511A, as well as 120 vial G4512A, the XL tray version. Those trays are also removable so that they can be easily swapped out, and you can actually have a continuous rotation of samples being loaded onto trays, in and out of the trays, and then on the bench top. You have integrated intelligence, which we'll get into in depth later, but that provides you with a wide range of method development options, as well as ways to improve your sample throughput and minimize the number of bad runs and downtime that you experience, even with operators who may not be experts in gas chromatography. And then finally, it is a scalable system that is meant to be in labs with a wide range of different systems. And so it's easily visible whether or not the system is running, when when the system is in park mode, as well as it provides a wide range of sample tracking options with a barcode reader and a cooling plate for temperature sensitive samples, particularly in food, alcohol, and dairy applications. Many folks will also ask, well, I already have a system with a liquid sampler on it. Why would I want to buy a whole different GC just to run Headspace samples? And the answer is you don't. Agilent has developed the transfer line interface accessory, shortened to XLSI, which allows you to run both liquid samples as well as Headspace samples on the same GC, on the same inlet. It is compatible with all of Agilent software as well as Empower, starting with Agilent 7890, excuse me, ICS v 2.6 for Empower 2 and Empower 3. And you can see the part number below for ordering if you would like to retrofit. That being said, it is important to note that this does require an 8890 or an 8860 or an Intuvo GC to properly interface, because many of the firmware and driver features do require the modern chipset that is in the 8890 and 8860 and Intuvo system. So with that, I'll hand off to my colleague Abby.
Okay, so let's talk a little bit about what is going on inside of our headspace. Okay, so what happens in our vial when the headspace starts its sampling process? So we want to make sure that we have equilibration between our sample and our concentration of analytes in the headspace. And so this happens in two different places. So once we put the cap on our vial, that equilibration step begins. So in some cases, that's adequate. In other cases, we need to allow a little bit more time. So while the standard equilibration will take place, once the vial is capped, we load the vial on the tray. And then as the vial is being moved into the shutter position, these are all what we would call ambient equilibrations. And that is what is taking place here. We can see that our concentrations are moving from the liquid, in this case, to the headspace. And so once our vial moves into the oven, we can set a timer on how long that equilibration needs to be optimal. So what we're going to consider with those parameters, we need an optimal temperature. So we need our oven to sit at an isothermal temperature that is adequate to drive this equilibration. We need to optimize how long that vial sits in the oven. And then in some cases, we need to agitate this vial to disrupt hydrogen bonds or disrupt certain principal bonds in the sample to force that equilibration. So our end goal here is to move as much of our sample, but not necessarily the solvent, into the headspace so that we can optimize our detection limits. The piece we're keeping consistent as we optimize this, we're generally keeping our vial size consistent, we're keeping our sample volume consistent, and we're keeping our solvent consistent. So we don't want to change too many things at once. So when we think about starting this process, that is the ideal place to start. So after we have reached our equilibration and our vial is still in the oven, we need to move it on to what we call the probe. And the probe is essentially a needle that pierces the septum. And this allows us to move on to the next step, which is pressurization. So we add an amount of gas to pressurize our sample higher than what the sum of the partial pressures are inside of the vial. And this allows us to open a vent valve and backfill the loop. And so our pressurization can be either nitrogen or hydrogen. Excuse me, pressurization cannot be hydrogen, it needs to be nitrogen or helium. And we can backfill this loop, which provides us with a fixed volume that we can now inject onto our GC. And so we need to make sure that we have enough flow within our sample path to adequately flush our sample loop with our sample contents onto our transfer line. And so an easy way to figure that out is we think of our loop volume, which is typically 1 milliliter, and then we want to divide that by the sum of the GC column flow and the split flow, because that's the total amount of flow that's coming through the headspace before it splits at the inlet. Okay. So how, method development can be, it seemed like a daunting task. It can feel very complicated. So what Agilent has done is we have included with existing calculators, we have added instrument intelligence that makes this a little more automated, gives you a little bit better starting points. And so we have a few examples of how we can use these tools to make that method development seem a little less complicated, or even just go through the calculations maybe before we start the method development. So with the Headspace driver, we have a couple of tools here. So we have one that we call the Method Development Wizard. So this has a couple of different cases where we can say either we want to build a method around a particular compound with a particular boiling point, or we can build a method around, maybe we found a method in the literature that we want to apply. So we can take existing valve and loop headspace parameters and generate a method on our 8697 or 7697 headspace. Or the third option is to take a pressure transfer method and move that into a valve and loop method. The second tool that we have in our pocket is called a method optimization tool. So this tool works with the sequencing within the instrument to increment certain parameters, one zone at a time, to evaluate the exact same sample. You prep multiple vials of the same sample, and you basically run an optimization. And so this gives you data that you can overlay and see which parameters had the strongest effect on your response. And so we can use this if we take an established method and maybe we need to tweak it for a new compound. There's a lot of use cases for doing this. We're always trying to press to make our instruments run as optimally as possible. But the desired output here is an optimized method that is robust and is designed around our analytes of interest. So as I mentioned, we have 3 method development wizards available. So we'll elaborate a little more on those. As I mentioned, the first wizard will create a set of parameters based on a specific analyte's properties. So we know what the boiling point is of our analyte, and we want to build our method around that property. The second is converting an existing valve and loop headspace method. This could be from another Agilent system. This could be from another headspace. This could be from the literature. So many options here. And then the third is to convert an existing pressure transfer method. And so the example here is based on creating a method on a specific application. So in this case, we've entered information that we are going to run a liquid sample. We are going to use a 10 milliliter vial, and that our sample volume, or the volume of our sample loop, is 1 milliliter. And for other properties, we're going to look at our sample in water. So water tends to be one of the more common Headspace solvents. And of course, that has a boiling point of 100 degrees centigrade. And then we're going to be looking for compounds, but our highest boiling point out of our mix, we're going to set for 200 degrees Celsius. So in this example that we're going to show data for, the sample doesn't quite need that boiling point, but I think for the sake of demonstration, we're going to push the system up to there to show how this tool can help you optimize. So this sample in particular is a mix of solvents and water. We have acetaldehyde, methanol, ethanol, acetone, isopropanol, and 2-butanone. So for the sake of example, we will take the parameters that were generated by the previous screen where we said we wanted to create a method based on solvents in water. And now we want to take those parameters and see if we can fine tune them to get our optimal response. So now we're going to move into the second tool that I mentioned. This is the method development optimization tool. So this is a little bit more manual, and it does require multiple runs, but I think the time is well invested in generating a more robust method. So we have 3 options here, 3 parameters that we can dial in. So we have the temperature, and this is referring to the Headspace oven temperature. So this is where the equilibration of our sample is going to take place. The second parameter that we can optimize is the vial equilibration. So this is how long we want to wait to make sure that that equilibration is complete. And then we can also evaluate the shaking. So we have shaking settings that can be incremented to see if shaking has an impact, if it doesn't, and at what point is the optimal setting for your particular sample. So we'll start with the oven temperature optimization. And in this case, we're going to increment by 10 degrees each run. We are going to start with an oven temperature of 55. So these were the parameters that our method development wizard gave us to start with. And we are going to increment by 10 degrees up to 200 degrees maximum. And so we've set some generous times. So we're doing a 7-minute equilibration. These were generated from previous application notes for the sake of the demonstration. But we can certainly go through and establish those optimal values as well. Okay, so one thing to remember is to consider the boiling point of your solvent. So this is one of the most important tips that I can mention. Headspace is based on the combination of all of the vapors coming off of your sample. So if you can control the temperature of your sample and select your solvent appropriately, you can minimize the amount of solvent that gets into your Headspace. In some cases, it can't be avoided and we just deal with it, but we want to avoid that solvent saturation if at all possible. So this is a result from my sequence of runs. Again, we have 1, 2, 3, 4, 5, 6 compounds, and we are incrementing the oven temperature. So the first number in the series is the oven temperature. This optimizer also increments the valve temperature and the transfer line temperature by an offset of 5 degrees, does that automatically. But the critical temperature here is the oven equilibration. And so we can see for the majority of our compounds, our greatest response was at an oven temperature of 85 degrees. And of particular note, again, we are dealing with water. Water has a boiling point of 100 degrees. And so we can see that the signal of our analytes ubiquitously drops once we've reached the boiling point of water. And this is because we now have more water in our Headspace than we do analyte. And so because there's a fixed volume there, the water kind of takes over and dominates our sampling. So this is why it's important to consider your solvent vapor in addition to your analytes. So now that we have established our optimum oven temperatures, so we can see the temperatures here are set at 85, 90, and 95 degrees. Now we want to see how long do we really have to keep our Headspace vial in the Headspace oven before we can do our injection. And so at this point, we're going to increment by 1 minute. So we're going to start at 0. Do we have to allow any time? Is our equilibration one of those that is super fast and we don't have to wait a lot of time? And we are going to increment by 1 minute to 11. So we'll start from 0 to 11 minutes and evaluate how long is necessary to get a maximum equilibration. So a little tip here, we have a concept called K. This is essentially how soluble your analyte is in your solvent. And so if you have a lower K partition, then you will need less time to equilibrate. Another way to think of that is if your sample is highly soluble in your solvent, you probably are going to have a high K. And so you may need to think about ways to improve that. But again, the same solvent mixture, and we can see at about 8 minutes, we have achieved our maximum response. So that would be the least amount of time that we would need to achieve that equilibration. And for most cases, it doesn't really change. You don't gain anything by having an extended equilibration. And so this would be the most efficient equilibration time to establish for this method. And the final manual optimization tool is shaking. And for this particular application, shaking had no impact, but I wanted to go through the screens to show you what that might look like. So you would want to make sure that you have your vial size correctly set, and then we would start at I think you have to start at a shaking level of 1, and then you would increment by 1 level up to the maximum shaking value of 9. And so this is a kind of a rotational shake. So this is almost like a very gentle vortex type of shaking movement, not an up and down or front to back kind of movement. So we're kind of trying to swirl and move things around inside the vial by agitating the oven. And so at the end of our investigation here, this is what a solvent mix looks like. So we settled on a Headspace oven temperature of 85 degrees. The 90 degrees and 95 degrees for the valve and transfer line came along as part of the optimization, so we didn't have to do those independently. We saw that the oven equilibration time was optimal at 8 minutes, and we did not need to apply any shaking to get a good response. All right. So now I will hand this back over to Adam, where he can talk about the sample workflow.
Thank you so much, Abby. So next we'll be taking you through the sample workflow that we've been working to optimize on the 8697 system. So sample workflows sounds like it's all the same, between different systems. But I think there's still definitely plenty of room to improve. So with a little bit of work from our R&D team, we've actually kind of designed the whole 8697 system around a simplified, fast sample preparation workflow to really make it as easy as possible to run your lab efficiently and handle really high volumes of samples when you occasionally have, say, contaminant in water or a major incident where a large volume of samples hits very suddenly. Sometimes this can really cause the lab to have a sudden backlog, and being able to work through a large number of samples very quickly is a really key feature to the 8697, particularly the XL tray with 120 vial capacity. So to start off, you load a new sample. The trays are removable from the system, so you can take it out, put all of the individual vials on, load up the vials, and then cap and then crimp all on the tray. So you're not having to try to do these with individual vials, and could potentially, have one tip over, spill, have a slight misalignment with your crimper causing it to leak. Just keeping it straight up and easily handled on the benchtop is a major feature, or hood, obviously, depending on the type of sample you're handling. Safety first, obviously. So next you take your sample and you go onto the system and run. You can then take an old sample tray that everything has been run, all of the vials have been punched. You can park it, you can swap out the trays, you can toss all of the old samples into the designated waste disposal, whatever is appropriate for that particular type of glass or contaminated glass. And then with that fresh tray, you can start back over again. So we oftentimes encourage folks who buy an 8697 system to go on Agilent.com or contact your salesperson and just add one or two additional trays to the order. They are very helpful for doing sample preparation while your system is running, and the system is designed to be able to park and swap trays very easily, just making this whole workflow a lot smoother. So if you are running, dozens or sometimes hundreds of samples, you need to understand at what point you need different types of crimpers. For smaller volumes, we recommend the manual crimper. This is, easy, low cost, simple, straightforward. It ships with every 8697 sampler. Just with steady pressure, you can squeeze to get the crimper to properly crimp, and then you can also have the adjustment valve or adjustment dial to make sure that you get a perfect crimp every time. For higher volume labs, we strongly recommend getting an electronic crimper. You don't want to potentially be trying to manually crimp hundreds of samples at a time. You're definitely going to get some really tired fingers. So we recommend this for steel caps. You can use also the high power option. You can use the plus and minus features to adjust the power to make sure that you get a perfect crimp without under or over crimping. And once you've gotten that dial set in, you can start running through the dozens or hundreds of samples that you have, all right there on the convenience of your tray. Just to go over, crimping best practices. A good crimp does not have any sort of deformation like you see in the middle where it is too tight and has that arch in the center, and then it also is not so loose that the cap can spin. You do need to make sure these are airtight so that the vial can be properly pressurized and does not have turnover of gas into the oven. So lastly, Agilent does provide a wide range of crimp and screw top caps. Screw top, obviously, for less high temperature, less volatile applications. And we also provide the highest quality low bleed septum material and high quality glass to really make sure that you get a consistent sample every time with the minimum risk of any sort of breakage, leakage, or other types of issues that you could be attributing to a vial. So Agilent provides the whole solution here for any Headspace laboratory. Next, we're going to talk about instrument intelligence. Abby went into a lot of detail around the method development wizard and the optimizer. These are really great tools, but more broadly, we've put a lot of work into developing the firmware of these systems so that you can actually have a lot of enhancements to the day-to-day operations right standing in front of the system itself, as well as connecting to it through your PC. So every system that the 8697 connects to, the 8890, 8860, or Intuvo, all have touchscreens which allow you to operate it. The 8860 does not have a touchscreen, but it would be accessible through the browser. But the touchscreen operation is a very, very convenient way of monitoring the system as well as navigating through a wide range of different issues. So with Headspace, there's some very specific maintenance procedures that can sometimes be new or challenging to an inexperienced operator, either someone who maybe is more used to liquid sampling or who is just new to the technique altogether. So with this, we actually have different types of steps that you can check and move through with visual guides and instructions and prompts, as well as automated pressure tests and other related functions that make sure that the system does most of the operational side for you, and you just have to manipulate the exterior components to work through whatever issue it is that you're trying to do or whatever component you're trying to switch out. Additionally, the Headspace has its own internal self-diagnostic tests, which minimize the amount of work that an individual operator needs to do to, for instance, perform a leak test or other types of checks on the system. It really makes it very easy, and the system will sit and walk through even the most inexperienced operator, just following the instructions so they can work through an issue. This is particularly helpful when you're troubleshooting an error or you have an issue and you just don't know what the root cause is. Even an inexperienced operator can at least do some initial troubleshooting to screen out some of the early easy causes before reaching out to a more experienced chromatographer or lead scientist to further try to troubleshoot an issue. You also see here some particular tests that are really useful, such as the vial leak test. This is really good for identifying the best settings to minimize leaks for the system. Additionally, you have with that connection and additional hardware and software connection between the Headspace and the GC itself. You have some additional options beyond just your traditional simple on-off options. You can go into specific sequence actions and reactions. If different errors or issues occur, you can change how your Headspace reacts to those issues. So for instance, having a vial missing can have a different reaction than maybe a vial size or a leak detection. All of these give you more options and let you cater the system and the method to your particular operations, and without just having an ambiguous, error message that you need to then go and troubleshoot. So on the system itself, you can also navigate through the browser or the touchscreen interface to the help and information section. This provides a lot of really useful content for operating the system, as well as instructions for certain different types of tasks. You can see here that the table of contents will take you to the various different manuals, operation manuals, user manuals, and many different types of information, logs, etc. These are really, really useful to identify potential problems, ensure that you're following best practices, and learn more information about your particular system without, for instance, asking, like we say, Dr. Google. So going through the help and information section on your system is a great way to identify all of the key documentation here. And additionally, you can go and log in through your browser by just typing in the IP address of the instrument through any PC that is connected securely through to the instrument. You're able to then go through inside of the browser with no software and navigate here and perform basic runs and tasks, as well as downloading a lot of this information directly to your PC, as well as the downloading the log, which can be very helpful if you're troubleshooting a more complex issue, and it will allow you to download and send it to Agilent Technical Support if you need it. So some really great features here and a really feature-rich set of information that we recommend every customer take a look at on their 8890 or Intuvo or 8860 system. So lastly, we went into a decent amount of method development and a little bit of theory here, but Headspace is a really deep and wide field with a lot of applications and a lot of development work that has been going into it for many, many decades. So we recommend that if you would like to learn more, you look up static headspace gas chromatography theory and practice from Golb and Etre. This will go into all of the different types of headspace systems, as well as a lot of the theory and practicalities of operating headspace system. Agilent also provides a lot of guides. The Headspace Sampling Fundamentals and FAQs on the Agilent website are great introductions to the technique and different types of applications. And then the Agilent 8697 Operations Guide, which is, you can see the publication number there, provides a lot of great details on the practical operation of a Headspace system, as well as the theory of operation behind it. So we're very thorough in those guides to make sure that you're well informed as you're trying to use your new Headspace system. So with that, I'll go ahead and pause and open the floor for questions. Both myself and Abby are available to answer.
Well, thank you both for that excellent presentation. We now have time for your questions. So our first question is, can I use the method development tools on my 7697 Headspace?
Hi, I can take that one. Yes, so the method development tools are part of the Headspace driver. So this plugs into to your software, and that's where these calculators live. So they will be on your 7697 Headspace and the 8697 Headspace options as well, as long as you have that driver.
Thanks very much, Abby.
Mhm.
So the next question we have is, how much volume do I need to add to a Headspace vial normally? Can I run a 50 microliter sample?
You certainly can. We see a wide range of vial volumes. And this is dependent on, most commonly we see 20 milliliter headspace vials, but we have seen, from microliter amounts where you're essentially vaporizing the entire sample, all the way up to 10 to 12 milliliters of water-based samples. So it really depends on the application. If you're looking for places to start, I would suggest if you go to the Agilent community, so this is a user-based community, and search for a software product called ScanView. So ScanView is a platform that allows you to search your compound, and you can search your technique, and it will go through all of the Agilent literature and pull relevant application notes. So you can see what's already been done. So if you're looking for something that may give you a shortcut, I would suggest starting there.
That's great. Thanks, Abby.
Mhm.
So the next question we have is, can I use an internal standard in my Headspace samples? And if so, which one?
Yes, I would recommend using an internal standard, just because there can be inconsistencies in the way you're crimping from user to user. There's a lot of variability that can present in headspace sampling, especially when you're learning the technique. So that internal standard can be an indicator on how consistent you are user to user, day to day. And as for which one, that really depends on what you are analyzing. I mean, ideally, you want to look for something that is not present in your sample, right? So I would start there. I don't know, Adam, do you have anything you want to add?
No, I agree. And I would just say that depending on the complexity of your sample, you may want to target particular compounds that would not come up. So, for instance, if you're using, say, an organic sample, something like a T-butyl group is extremely rare in normal metabolisms. So, having, say, a T-butanol or a T-butyl ester can be a really good place to start. to make sure that you're just not getting any sort of potential false positives or secondary signal from something that has entered the sample. So yeah, the biggest thing is just to avoid a compound that might potentially pop up in an occasional sample under unusual circumstances.
Okay, that's great. Thanks very much. So another question we have is, when using HSSPME GCMS, how can we calibrate the system when analyzing volatile organic compounds from fabrics, for example?
I love these kinds of questions. They turn my turn my gears. So I haven't done this application specifically. But typically, I mean, the easiest answer is you have to find a fabric that is certified clear and then spike it. I mean, that's the ideal world, right? But that's not always realistic. So the best approach is to find try to define like what a background would be, and then you have to kind of do some manipulation on your numbers to subtract what that average is. So it does get a little dicey. Volatiles are prevalent in a lot of different areas, so you have to make sure that your sample prep station is clear from volatiles. So something that I would recommend there is to just cap some vials that are left out in ambient air and analyze to make sure that you don't have the presence of volatiles in your ambient environment. We see issues with this. At one point, we were prepping our volatile sandal standards right next to a solvent cabinet and getting really strange results. So always be aware that volatiles are tricky to analyze through any technique. I always recommend starting to analyze your air around your sample prep, and then really characterize what your fabric sample in this example, what's there and what's not. And then you can always use an internal standard and use that as a correction. So hope that
Oh,
helps.
yeah. Thanks very much for that explanation, Abby. I think
Hmm.
that will help a lot. So, next question is, what if your analyte BP is higher than your solvent BP? Do you switch to a higher BP solvent?
If you can, that would be the best approach. Otherwise, there are chemistries that you can put in your sample to make a less volatile analyte more volatile, without knowing exactly what you're looking at. A lot of people will add salts, or they will add different compounds to do things like disrupt hydrogen bonding to try to promote a lot of those compounds up into the headspace, um, to uh, to get a better detection limit. But ideally, I would start with the solvent if you have that ability.
Okay, thanks, Abby. So, next question is, can we reuse Headspace vials?
Yeah, I would advise against it. I know that sometimes we face budget constraints, and that type of thing is problematic, especially for research labs, academic labs. So if you have to reuse the vial, you clean it and then certify it with your headspace that you actually did get it cleaned. But always put new caps on. So again, I strongly advise against it, but you need to verify that your cleaning process is good, and always use new caps. I don't know, Adam, you have comment on that one? I feel like I'm.
Yeah, I would similarly not recommend
Yeah.
reusing it. One additional aspect that would be concerning as well is potentially the physical robustness of the vial.
Hmm.
Given that if you are crimping that vial, you're applying a decent amount of pressure to it, and then you've also thermally cycled it,
It's true.
and you would not want to potentially have that vial rupture either on the benchtop when you first crimp it, or even worse in the oven itself, leaving having forcing you to have to open up the instrument and clean whatever was in the vial out. Which, considering that many of these samples are very dirty, wiping that out of an oven that was hot and has dried out and has caked onto things, at a certain point, it's just worth buying new vials. I'll have to say, there's other ways potentially to reduce costs.
Thanks, Adam. Thanks for that contribution. And the next question is, how do you rate repeatability in method development? How many replicates do you suggest?
So repeatability typically for Headspace, I think most methods require somewhere between 5 and 10% RSD. The number of replicates varies. Personally, I think you need a minimum of 7 to be statistically relevant. I typically do 12 for methods that we publish. But while I'm actively developing the method, I typically run more along the 20 to 25 replicates, especially with Headspace. I am not the world's greatest crimper of vials. I struggle sometimes to get my crimper dialed in. And so I like to have a larger data set so that I can make sure that I crimp the vials right and that I've really dialed in all my parameters. So depends on how much time you have. I typically have a little more time to develop these things than many of you have in the real world. So I will run as much as I can to get good data and to make sure that my parameters are really dialed in.
That's great. Thanks, Abby. So another question we have is, at the beginning, it was mentioned that the volume of vial and amount of sample need to be optimized. How do these two parameters affect the analysis signal? If equilibration is reached in a particular volume, then shouldn't the signal be constant?
So there are a couple of variables, and I'm not fully sure I understand the question. So if the vial size and the sample volume are consistent, then you can draw your conclusions from that data. If you're changing the volume of the sample, you're also changing the amount of vapor of space that can hold the partial pressures of your analytes, which is the part that we're actually analyzing. So that's called the phase ratio, and that gets into the theory of headspace sampling. Um, so that needs to be consistent. So I agree, if you have a sample of the same concentration, same volume, in the same size volume, or a same size vial volume, then yes, it should be consistent. But if you're changing either of those parameters, then the signal will not necessarily be consistent. So that would have to be evaluated. So that's why
Yeah,
we say standardize the vial size and the volume of sample to
I can
begin the optimization.
I can jump in here as well
Yeah,
because I'm
go
looking at
ahead.
this a little bit.
Hmm.
I think that there's a base assumption here that whatever is actually vaporized is not a significant has not decreased the concentration in the liquid phase significantly by having that compound vaporized. So you would assume that if you have like 50% water, 50% ethanol, and then you look at the same, and then you look at the amount in the headspace, you can have a pretty wide range of volumes, and it's really not that much vaporizing where it would change the concentration in the liquid. But that's not a valid assumption that you have constant values when you have very low concentrations of a particular compound, especially if you're adding salts to the solution. So if you only have maybe a few milligrams or micrograms of a particular compound in solution, and then you're also using salts to drive them into the vapor phase, you're also heating it up to drive it into the vapor phase, you can appreciably reduce the amount of sample or in the liquid phase by driving it into the vapor phase. And so you're having a constant amount of sample, a constant mass of sample, and then you're varying the volume inside of the vial headspace by varying the liquid because you're displacing that gas phase with liquid phase by changing it around. So the assumption that in equilibration is always going to be constant in the vapor phase is not valid for those very low concentrations. It's kind of more valid if you have a very, very high concentration, like I said, 50-50 or 90-10. When you're getting into the low values, it's not a valid assumption. So this is getting into headspace theory, and that would be I would really recommend going and reading over at least the operations manual that we put together, or the publication that we recommended earlier, Stagger Headspace Chromatography Theory and Practice by Kolb and Etre, E-T-T-R-E. That's a really good resource if you want to dig into experimental design in Headspace. Just take an afternoon, you read through the introduction, and it'll go through, and you'll see whether your assumptions are valid for your particular case.
Okay, thanks very much, Adam. Right, we have a very kind of specific question here. So here it is. How do I know if my Agilent Headspace transfer line has the Pro Steel sleeve? And it's part number 41770607. If not, what is the maximum temperature I can use for the transfer line?
Yeah, so I don't remember the max temp off the top of my head, but I can follow up with this one in email. If you have the sleeve, you should be able to see it when you pull. I mean, you'd have to release your transfer line, but it should be coming out of the GC side of your transfer line. So it's just it's a, I believe it's like a light tan color, and it goes around the metal right at the exit of the transfer line. So you should be able to visibly see it if you pull your transfer line out of the inlet. But apart from actually taking it out of the GC, I don't know of a way to determine that.
Okay, thanks, Abby. So next question is this person says they like the features for the method development. Commonly, they use the GC for residual solvents 467. Is there a relevant application note about this topic within the instrument?
I'm not sure which instrument you're running on, but we do publish USP 467 application notes on just about every product. So I would say go to agilent.com and find the Headspace unit that you are currently running on, and you should find another application note that shows performance.
Yes, so if it was an instrument that was manufactured in the last 10 years, you definitely should be able to find the residual solvents application note. You may even find it for multiple different detector setups. So yeah, 467 is a very well covered method. Just type in your Headspace model number and then USB 467, and you should find it very easily on Agilent. And if you have any trouble, just send it along to us.
Okay, thanks very much. And I think we've got time for one more question, which is in a 20 milliliter vial, would a 10 milliliter sample volume be okay?
Yeah. So I have a rule of 50% with 20 ml vials. I think you can go a little bit more. The one thing to monitor for is if you are doing a lot of shaking. So if you have to really agitate your sample on high levels of shaking, you might check for contamination just to make sure that that shaking isn't contaminating your probe. So run blanks and make sure that your system's clean after you run a sample. But no, there's many. I think volatiles in water uses a 10 ml sample. There's several well published applications out there that do use larger volumes. So totally okay in a 20 milliliter vial.
Excellent, thank you. So yes, I'd just like to thank you both again. And if any other questions do come in, I'm sure that Adam or Abby will be happy to respond to them via email. I'd also like to thank our scientific partners in this webinar, Agilent. And with that, I'd like to thank you all for logging in and listening. Thank you and goodbye.